Well, good afternoon or good morning, depending on where you're located today. Kathy, you can see my screen okay?
Yes, we're all set.
Okay. Okay, so using root cause analysis to identify and prevent problems, and certainly in concrete, there are daily challenges that we face from operational sides and the quality side and delivery and just about every aspect of our business. You can have issues that while we have to solve some of them right now on the spot, what we want to do is identify root causes and keep those things from reoccurring on a regular basis. So we'll jump right into it. And the first thing we want to really touch on is the fact that if we have a process in place that helps us address problems, then it's easier, first of all, to get to the solution. And then it's not a fire drill or a panic situation. We know the process. We know what we're going to do. We have these things lined out, and we can take a calm, systematic approach to getting the problem solved. Now, that doesn't mean that on occasion everyone's hair doesn't catch on fire and we have to put things out, but in general, we want to have a process. So that's going to involve some input. The more input I can get when solving problems, the better off it is, and usually from more than one person. I'm going to process that input. Now, that might mean that we set up charts, we set up spreadsheets, we look at data, we do a statistical analysis, we do a lot of things, but in some fashion, we're going to process that. Then we'll have some output, and then really importantly is to get some feedback. Working in a vacuum, thinking we've solved a problem without actually discussing it after the fact and making sure that we address everything that occurred is usually a remedy to have that problem occur again, or to think we've solved a problem and not really have reached that solution. So we want to get feedback anytime we're involved in a problem situation. So root cause analysis. So I think everyone's familiar with the term. It's really a method of problem solving for identifying the root cause. So what is actually at the bottom of what I'm dealing with? A factor is considered a root cause if removal of that from the sequence prevents the outcome from reoccurring. If it's a causal factor, that's one event or one effect of an event's outcome, but not necessarily the root cause. So removing that certainly is a benefit, but it may not be the root cause. So for instance, if I have air fluctuations, and everyone's dealt with air fluctuations, adjusting the air entraining dosage is causal. So that gets me where I need to be right now, but that doesn't address the cause of the variation in my air. So developing a system or putting a process in place to find out why my air is fluctuating, getting to the root cause of that fluctuation is what I'm looking for. Okay, so that's what I want to do. I want to get to the root cause. I want to get to the bottom of it so that I can avoid a similar problem the same day, the next day, a month later, whatever that may be. So we want to get down to the bottom of it so we can stop these things from happening. So troubleshooting is something that occurs in a precast plant every day. There's something that happens that we need to address, something that's going on, whether it's bug holes, whether it's slump air, whatever it is, it's something that I have to deal with right now so I can continue production. So it's not something that I can spend a lot of time putting charts together, reviewing it with a lot of people, something that I need to address to continue production. So that's what we call troubleshooting, and that's a good name for it, so that we can get things done quickly and move on with our work, continue our production. Problem solving, if we can differentiate that, is a little more complex. again, we're looking for some data analysis. We might have a team involved, and that team could be QC operations, could be QC and delivery, could be more than one QC person, but a team approach is always good to get different perspectives on what the problem is and how we can get to a solution. It could be a process situation. A lot of times in concrete, we focus initially on materials. Is it a cement problem? Is it an aggregate problem? But the processes involved are just as important and sometimes more important than the actual materials that we use. So we want to look at all these things, all these factors in our problem solving. And then process improvement. So that's an ongoing activity. And this, a lot of times, involves small changes to continuously improve. And this takes a lot of dedication, I guess, from the entire team. And we've all heard the term total quality management. I think everyone has their own definition of that, and I'm not going to put an official definition up here for that. But essentially what that means is that we're all working together to make things work the way they're supposed to. We know that what the outcome is of what we're trying to do, and we want to get there. So we want to have process improvements so that we can continually improve both our process and our end product. So when we go from troubleshooting, that's that on the spot, give me a solution right now, I need this to keep going, problem solving, again, a more detailed, involved process, and then the daily activities to make sure that the things I'm doing gives me the quality that I'm looking for. Okay, so troubleshooting, and this is a very common example. In fact, this actually just happened within the last month. A producer typically uses 4 to 7 ounces per yard of an air entraining agent to get 5 to 8% air. On this day, they're using 40 ounces a cubic yard, and they're only getting 2.5% air. So we get the call, and there's a lot of things going on, but this is something that we can't say, well, we'll set up a meeting, we'll look at all the data. No, we have to have a solution today so they can continue producing concrete. And so we had a lot of discussions, probably half hour on the phone. We're talking, and I said, okay, let's run a very simple test. And so we run a very simple test. We take some fly ash, and we're not picking on fly ash, but from the conversation, it seemed like fly ash might be an issue. So we have some fly ash here. We put it in a bucket with some water, and we stirred it up real good. And lo and behold, we have a lot of carbon that comes to the top. So now I know what my problem is. I have a fly ash delivery that has excessive carbon, 40 ounces a yard is only getting 2.5% air. Chances are I'm not going to be able to get the air content I need using this fly ash. So the solution to this, for this particular producer, was to go to a mix that didn't have fly ash. That's not always a solution. In some cases, you might have to stop production until you can get another fly ash in if fly ash is required. And this is just an example of troubleshooting where on the fly, if you will, we needed to solve a problem. So we reacted, we ran a very simple test. There is no ASTM test method for this bucket test. So we run a very simple test, and then we get a result based on what we thought might happen. And we were fortunate enough that the first thing we tried here revealed the problem, so we moved on. Now, after this, there's some process improvements involved with this particular producer to address this not happening again. But on this day, for this particular instant, we just needed to solve the problem for today. So that's just an example of when we talk about troubleshooting versus problem solving, and this is a perfect example of troubleshooting. So getting information, input. This is where we start with the process. We define the problem. Now, in the last example, it was a very simple definition of I can't get air no matter how much air and training agent I put in there. So it's a simple who, where, when, what, how, and why, and we'll go through this in a little more detail. But we want to ask as many questions as possible. In my daily job, when I deal with problems, someone calls me and they've dealt with me enough now that they have a whole list of things that they'll tell me because they want to avoid all the questions that I'm going to ask. So not a bad thing to have a process set up where you know what questions you're going to ask and who you're going to ask those questions to when a problem occurs. So just some suggestions here. The who's the plant operator? Now, I'm not pointing fingers in any direction here. These are just questions that you can ask. Is the plant operator new? Is the loader operator new? Do the failing test results occur more common with a particular technician? So the who is involved in all these things is important. Where, and again, in a precast plant, where's the bed relative to the plant? Do I have a very long travel time to get there? What's the environment? Am I inside or outside? So the where of this, where is it occurring? And almost as important, or just as important, is where is it not occurring? So we don't want to have only bad information. We want to have good information. And then what time of day? We've seen more than one occasion where a plant's running 2 shifts and a lot of problems occur as they change either the placing crew, change the plant operator, change the loader operator. So what time of day does that happen? Is it a weather issue? Traffic's not so much an issue in a precast plant, but there are some precast plants that do cross the road to get to the other side of their yard. So when does it occur? And Monday is a good question, more on the ready mix side than on the precast side, but Monday is a bad day to pour concrete in the ready mix industry. And then what type of structure? What's the importance of the structure? How was it placed? How was it mixed? How was it finished? How was it tested? All these things that you can be asked. So if someone says to me the shrinkage was too high, and this happens occasionally, and then the first question I asked was, how did you test for shrinkage? Testing for shrinkage in the field is a bit problematic, so that's one of the first things I would ask. So again, there are a lot of other things we could ask here, but this is kind of a starting point. This is a place where I go. Invariably, if there's an ongoing issue in the plant, I always want to talk to the loader operator. He sees the materials day in and day out. As far as aggregates, I want to know what he thinks about what's happening in that with those materials. And then why? Why is this happening? You know, we could all throw up our hands some days and say, why? Why does this happen to me? Why am I having this problem in my plant? Well, unfortunately, it's concrete, and while we don't always know the why, there are certainly ways we can get to the why. So I want to review all the information. One of the first things that I think should happen is just check the mix and the yield. So is it proportioned properly? Are the materials put in the batch computer correctly? You know, if I have a complaint about someone's telling me the mix is too bony or too rocky or something like that, you know, just check it. Let's make sure that the mix is put in properly, that it's yielding properly. And then, do I have performance data over time? It's always good to have control charts, both for slump, strength, unit weight, and air contents. If I can track those 4 things over time, then I can get a very good picture of how the mix is performing and when that performance changes. One of the things that I like to do when reviewing information is compare unit weight to strength results. If I have enough data, I can almost tell you that at a certain unit weight, if I go below that weight, I'm not going to get the strength that I'm looking for. So I want to have that data over time, and as much of it as I can get. Review the test reports. Again, that may seem obvious. Review the batch records. And then this is somewhat frustrating when you're really trying to solve a problem quickly. But if you do make changes, let's make one change at a time. So I eliminate one variable at a time. If I change 5 things in my process or 5 things in my mix, then I don't know which of those 5 things solve the problem. Now, again, in some situations where I'm just not getting the performance I need and I need to get a change, you may go in and make wholesale changes to the mix or to some process. But in general, I want to change one thing at a time so I can identify what that impact is. So change one thing at a time. I want to check the plant and delivery equipment. Doing a process review of your plant and your processes, your equipment on a regular basis is a good idea. So you can set up a very simple spreadsheet, checklist, if you will, and some people would refer to it as a plant audit. And you know your plant as well as anyone. So go through, check your mixes, look at the materials, check all the batch weights, were all the proper procedures followed, is the equipment in good shape, and then talk to the driver. Now, different plants use different delivery units. Some may use a tucker, some use ready mix trucks, some of it goes straight into the bucket. Whatever that delivery unit looks like, the guy that's delivering that concrete on a daily basis a lot of times has a lot of insight on what the concrete looks like. Did it look normal? And I know normal is a bad word to use, but what did it look like? The age of the concrete, was it in the mixer longer than others? Did it sit in the tucker for a while? Did it sit in the truck for a while? All these things come into play. If you're in a ready mix truck delivering in the yard, added wash water, or even added wash water in the plant. Mixing time can be a huge factor with a lot of variables, including slump life, and air contents. Worn blades in the mixer or buildup on the mixer blades will oftentimes impact what happens with the air and the slump. And then the batchman and the loader operator. So the 3 highlighted in red, those are the people in the plant that I always want to talk to when investigating a problem, because they see the concrete, they deal with the concrete every day, and concrete can often be very visual, and these folks will notice things that are different than they were previously. So collecting that information from these folks is a good part of the input. And then at the bed, the placing and finishing crew, talk to those guys. And again, they will often notice something different. Placement conditions, what was different or unusual. Many times I ask the question, well, what was different about the concrete on this day, whatever the problem might have been? And almost always the initial answer is nothing. But then after a little more conversation, then we get to maybe what appear to be some small things. But if they notice something different, then that's good to note. Again, weather at the bed, curing and protection procedures, test specimen fabrication and storage. And sometimes this is It has to be done at the bed. Sometimes those are done at the QC lab, but it's often something worth looking at. And then sample transportation. In a lot of precast yards that are larger, samples are made at the bed, transported back to the QC lab. If that span between casting and transporting is too long, that can often cause us problems. So again, these are some things to look at. And then on the QC side, what do my test procedures look like? Is my equipment calibrated? Do I have qualified technicians? And then am I keeping good records? And these are all things, again, that are common sense things that we need to follow. Okay, so one of the things that really helps when you're solving a problem is to have, again, a process. So when we look at some of the Six Sigma stuff, and you could spend a lot of time going into the Six Sigma processes. A lot of it is process oriented, more so than what we deal with a lot of times in precast plants. But still, one of the big things that we get into is focusing on a problem so that we can solve it. So there's a couple of methods we could use. We can use the DMAIC, so we'll define it, measure, analyze, improve, and control, which again is basically a root cause analysis. Some methods for analysis that we're going to talk about today. 5 whys. This is a favorite of mine. I like asking the question. Someone answers a question, and it's very easy to say why again, and we'll get into that. It sounds very simple, but again, when we're trying to get to the bottom of a problem, we are often stop short of where we need to be to find out what the problem is. So we'll get 2 layers deep and we should have gone 5, or maybe it's even 10. So there's often a much deeper issue than just the basic problem. And then the fishbone diagram, we'll get into that, and that's a very useful tool again for ongoing problems. So first thing we need to do is we need to define the issue, right? So define the problem. And then we're going to measure. So we're going to measure the existing performance. We're going to analyze that data. And hopefully find the root cause of the variation. Again, on paper, this sounds very simple, right? We all know that concrete is very complex, and what happened yesterday may not happen today, and if it happened today, it may not happen tomorrow. So we know that we're going to have variables in our production, but we need to control those as much as possible. And when we're having an issue, which of those variables is causing me the problem? So then I'm going to analyze all my data. I'm going to improve my processes, and then I'm going to control that. And this gets into the process improvement. So I want to be able to do all those things, and this kind of helps me think through these problems. So I need data, I need input, and I need everyone to be on board with what we're trying to accomplish here. Okay, 5 whys. So peeling away at the symptoms of a problem. That's an easy way to say it, but really what we're saying is we want to determine the relationship of all these things to each other. You know, when we talk about air, someone asked me, well, what impacts air? Well, someone else gave an answer of, you know, if you close your eyes and open them, whatever you see impacts the air. So essentially everything does. So when you're trying to solve an air issue, getting to the root cause sometimes very problematic. So we want to continue to ask questions. And this is simple, but it's not necessarily easy, right? Because asking questions and getting answers, first of all, we have to ask the right questions. And then sometimes we get answers that are incomplete, and we can easily go down the wrong path because of some answers we're giving. So the more questions that we can ask, And frankly, sometimes the questions I ask are of myself. So I'm looking at an issue and I'm asking a question about why this happened. I'm giving myself the answer. And then when I get through that, I need to make sure that all of that made sense. I have a very simple rule that I follow. If something doesn't seem to make sense, then it probably doesn't make sense. Very simple. Okay, so again, I want to just walk either myself or someone else through why this happened. Oftentimes, again, in the middle of a placement, we're trying just to get through production, and then we come back after that and say, why did this happen, and how can I keep that from happening again? It is very useful when problems involve human factors or interactions, and everything we do with the concrete and the concrete plant, whether it's handling the material before it gets in the mix, batching the mix, mixing the concrete, placing the concrete, consolidating it, finishing it, all of those involve a human factor. And it's obvious, but you don't need a project. So again, this can be on the spot. Let's dig into this right now. I don't need a project to make this happen. So here's a very simple example. Not that I've ever gotten a speeding ticket, but if I got caught speeding, why did I get caught speeding? Well, I was late for work. Well, why was I late for work? Because I got up late. Why did I get up late? My alarm clock didn't work. Why didn't my alarm clock work? Because the batteries were dead. And why were the batteries dead? Because I forgot to replace them. That's very simple. But I could stop at, I got a speeding ticket because I was late for work. But that really doesn't solve the issue of getting the ticket, right? Because I've got to go all the way back to, I needed to get up earlier, not to be late for work. Now, the solutions given here, get an alarm clock that plugs into the wall. That's again, pretty obvious. But one of the things that might apply to some of the things we do is to replace the batteries at set intervals. So some of the things that we do in concrete, we could say, I'm going to do this at a certain number of days, whether that's running tests on my aggregate, whether it's running tests on air. I know a lot of plants do that first thing in the morning and so many yards through the day. So there are some things that we can put in place to avoid things happening. And again, this is a very simple example of something we can all relate to. So one of the big issues I think that we have is getting the problem defined. Oftentimes, the initial problem that I hear from customers is not the actual problem. So for example, someone says to me, my concrete's going off. No, I have to find out exactly what going off means before we can start looking at the problem. So for some people, going off means I'm losing slump. For some people, it's setting too fast. So I really have to dig into, what do you mean by going off? So I can't just jump into it until I clearly know the problem. And again, when we say write things down, we're talking about I have an ongoing problem that I need to solve, right? And then I'm going to ask why the problem happens. So I'm going to give an answer, and then I'm going to say why. Why did that happen? Now, you may do this in one question. It may be why, and then you get an answer, and maybe that's it. In concrete, it usually doesn't happen that way, but certainly it's possible. And then keep going, and again, it could take 5 times. It might take 10 times. Hopefully not, but it may not take 5, maybe less than that. And then when you get to the end, if you look back at the answers that you got, you read it back to yourself, then it should make sense. So all of these steps were logical and got you to where you needed to be. And then if we want to look at having the multi-legged, now this just says that I've got multiple issues here and I'm trying to deal with all of them. So I've got a product, I've got a process, and I've got a system. So let's just say, for example, I have a architectural panel that was supposed to get a light sandblast, and instead it got a very heavy sandblast. So the sandblasting worked perfectly, right? Somebody did a heavy sandblast. So now I can look into why this happened. Why did I get a heavy sandblast instead of a light sandblast? And then I can say, well, why wasn't the problem detected early in the process? So how did it get to that point, right? And then if that panel gets delivered to the job site and the customer says, you know what, that panel is not correct. It doesn't match all the rest of the panels. So then how did that get to the job site before it was caught? So I've got several issues here that relate to the same problem, right? But I've got different root causes for each of those. So I'm going to have a root cause of how did it get the heavy sandblast in the first place? How in the world did it get to the customer? And then what in the system failed here that allowed me to do that? Okay. So again, writing it out in this manner, drawing it out in this way, that's something that if you wanted to do that, you could do that, but it's not necessary. A very simple notebook, writing the questions down and the answers works just as well. Okay, so here's another example of a concrete issue. So this is something that everyone in the ready-mix or precast or pre-stress industry has dealt with at some time, is air and train concrete. So in this case, while testing the air and train concrete as part of the routine activities, the technician notes that the mix has been performing inconsistently, inclusive of slump, air, and density. So the mix has been performing inconsistently. That's much too broad of a question, right? So we say, why is it doing that? Of course, I don't know is not the right answer, even though you could say if we knew, we wouldn't be asking the question, right? So why is it doing that? So again, it's very open-ended. Let's be more specific in this area. So why is the slump inconsistent? That's a reasonable question. The slump's inconsistent because there are different amounts of water in the mix. Now, there's two things you could say here. This is logical, right? If the slump is inconsistent, it's because there's different amounts of water in the mix. That makes sense. However, I really need to look into some things to make sure that that's correct. So I need to go look at batch records, talk to the batch guy. And so it's not as simple as I can ask a question and have an automatic answer, right? I need to find out. So I know this to be the case in this case. It's not variable amounts of high range or anything else. It's different amounts of water in the batch, okay? So I get that answer. So why is the water content changing? Again, this is a logical next question based on the answer to the first one. So the batchman has to adjust the water content manually by the load. Now, again, there's a couple of ways you could go here, because first of all, why does he have to adjust manually is one question. Why does he have to adjust at all is another question, right? So there's something happening here that is causing a problem. In this case, why does he have to adjust manually? Because the moisture probes are broken and haven't been fixed or replaced. Okay, this is a problem that's happened in most of our plants, right? So I have these moisture probes, they're not working. Now I've got to adjust manually. So why haven't the moisture probes been fixed? We're too busy. We didn't have time to do that. Why haven't we had time to fix the probes? and this is a circle we all get into, right? We're trying to do production, we're trying to do it quickly, and so now we've made this decision, and often it's not a conscious decision. We didn't say out loud that, you know what, we're too busy to fix the probes. We know we're too busy, so we just don't do that. So we've sacrificed some quality to meet production goals, but in the end, you know, did we really do that? Because now we're going to be slower in our production. We might have to recast some of the products. And again, this is a very common example, and it is just an example. You may never experience this in your plant. So here's one that isn't in your handout. I added it later. So if we went through this, and I have low compressive strength. Now, this could be a release strength, could be stripping strength, could be whatever, but we have low compressive strength. Okay, so the obvious question is, why was the strength low? Okay, so because the water cement ratio was too high. Now, too high is a relative term, right? So we understand that it's higher than specified, maybe. Doesn't mean it's going to be low strength. So what we're saying here is that this mix, this batch that had low strength, had too much water in it, and we have discovered that by some fashion, right? This is another case of why was the strength low? Oh, because it's got too much water. You know, I don't know that until I do some work to find out why that is. So if I know that the batch had too much water, now that makes sense. That would impact the strength, but I need to determine that. And we're not going to talk about the tools that you would use to do that, but we've determined that in this case, that's the reason. So why was the water cement ratio too high? Because the plant operator added water to the batch. Okay, so that makes sense. He added water to the batch. Why did he add water to the batch? Because the placing crew foreman asked him to add water. Okay, fair enough. Why did he ask him to add water? Well, because the mix was very sticky. Now, this all makes perfect sense. And I can tell you that I stuck this in here because I just went through this with a customer within the last week. And so there's a lot of questions you could ask next. And of course, that's the next question is, what would I ask next? So I can go a lot of directions here. Obviously, the next question is, why was the mix very sticky? Well, in a lot of cases, the mix is sticky because you need very high early strengths. So you have low water cement ratios, you have high powder contents. I think I would go beyond that and say, why did the placing foreman think it was okay to add water to the mix? Why did the batch guy think it was okay to add water to the mix? And then you can get into the whole point of what could I do to this mix besides add water to make it less sticky? Because sticky concrete is no fun to place. In some cases, we're going to be stuck with that. In other cases, we're not. We're going to be able to work through it, come up with a solution. But this is common. This happened again within the last week. So I put this in here. And the answer to the question in the real case was the plant wasn't used to placing mixes of this type with the high strength. Sticky mixes to them in the past were just because the mix didn't have enough water. So when you get right down to it, the root cause here was a lack of training or communication to the batching and the placing and finishing crew to let them know this was a new mix, was going to be sticky, was the nature of the beast, so to speak, and that's what was going to have to happen. That wasn't done, so they went about this in the way they normally place concrete. So we're going to ask five whys at least 5 times. And again, in my experience, sometimes I'm at 2, 3, sometimes I'm more than that. And because we've always done it this way, absolutely is not a root cause. Okay. that could be an issue of getting things to change, because let's face it, most of us don't like change, but we've always done it this way, is not a root cause. It's not a good answer to why we do something. Fishbone diagram, this is a cause and effect. So in this case here, it's very simple. I've got a problem, which is the effect, and then I've got all the things that impact that. So in this case, there's equipment, there's process, there's people, materials, environment, and management, and then there's going to be smaller bones off of that to give me a clear visual, if you will, of why the problem is happening. Now, I can assure you that when I draw this out, it doesn't look nearly as neat as what's on the screen here. Don't get concerned about that. Use this in a way that helps you solve the problem and think through what's going on, and not try to be perfect. I have a hard time drawing a straight line, so mine do not look like this. Okay, I'm not going to spend a lot of time on here. This is in your handout, so this is basically just telling you how to put this in place, and I'm going to jump ahead to this slide where we're going to talk about missed free throws, or the Shaquille O'Neal effect. And while this is, again, this is a bit silly, if you will, this shows all the things that go into a missed free throw. The only thing that's not here is that you're just a bad shooter. So all of those things come into play, and I can assure you, if you've played basketball before, you've probably used all of these as an excuse to miss a free throw, or that you didn't make a shot in general. So you just get an idea here of all the things that are in play when you start talking about why there's a problem. And you can even see the Tom Brady issue here with deflated ball that causes you to miss, which is actually a true statement. If the ball's too flat, it's hard to shoot free throws. So again, this is an example. Now this is something that I've put together in my computer just so I can have this and write some things down, and this is mostly blank, but I've included all the things that typically come into play with a rejected load of concrete or rejected batch of concrete, starting with the order, or in the case of a precast, did the right mix get ordered from the placing crew or assigned to it, to that project. So something I have in my computer, it's easy to put this stuff together, much easier in the computer than it is for me to draw it by hand. So once we've done all these things, we've gone through these processes, and while it sounds very simple and looks very simple on the phone over the computer, it's really not that simple in most cases. So, but I've solved all my problems now. My day is good. My week is good. I have no issues in the plant. Now, I need to make sure that they don't come back. So I have to have controls in place, and controls, while they may seem rigid, often need to be flexible based on changes in both materials, equipment, and even staff. So I want to have these controls in place, but I want to be continuously examining these controls themselves to make sure they're what I need to continue to solve problems. And we know that when we get through one problem that you know, I may think I'm good, I don't have any other issues. Eventually something else is going to pop up. Just the nature of our industries. So we want to avoid problems instead of solve problems. So having these programs in place is good. One of the things that is extremely important that probably doesn't happen enough is someone has an issue. Really, you should grab samples all the materials at the plant at that time. As materials come through and are used up, we see problems come and go, and we don't know why they happened. We don't know why they stopped happening. We really don't know anything about it. So when you have a problem, grab some samples immediately, okay? And the other side of that is when you're not having a problem. So I'm having a problem. Let's stick with the air variability. You know, I have a day where the air is all over the place, so I grab samples of all my ingredients and I set them aside. The next day I have no air problems. Well, I'm going to grab samples of those ingredients too, and I'm going to do some comparison testing, see if there's a difference from one day to the next. So grab some samples when you're having problems, and then grab some samples when you're not having problems. Oftentimes a problem is not discovered until later, right? Hardened concrete, for example, the strength issue that I gave earlier, that usually doesn't show up until later on, and oftentimes it's not a one and done situation because the problem was recurring, but we don't know it for 28 days or 7 days. If it's a release or a stripping strength issue, then we know that fairly quickly. But a sample of the quote bad concrete and a sample of the good concrete, if you're going to do an investigation, is very important. So we want to have all those samples. Question often comes up, how much of a sample should I collect? Well, enough to run the necessary tests. And if you don't know all the tests that may be run, then you know, there's plenty of information out there. I'm sure that you can consult with someone to let you know about possible tests, whether it's petrography or whatever it may be. But whatever that is, you know, get about twice as much as you need for that test. And then don't be afraid to, and I know production is important, but oftentimes if you can delay the batching or just stop it for a very short period of time and collect those samples right then, it's really helpful in avoiding those problems in the future, which in the end helps production to keep going. And then keep the materials in a dry, airtight, sealed container. We recently had some concrete delivered to our lab from Europe, and it was some concrete that was 2 weeks old that had not set up, and so we actually put that in a sealed bag and then put it in another container, shipped it to our lab in Cambridge, and when the concrete arrived, it was still plastic. So we were able to look at that in the state that it was in, and ultimately determine why the concrete was retarded for 2 weeks. Okay, labeling, you know, when you took it, where you took it, what the project name was, sample description, all those types of things are very important. So at the end, we can summarize this by saying we want to have a process. We want to be able to clearly go through all the processes that we have in our plant, go through the materials, how the materials are handled. But we want to have that same process for all of our problems. Now, we think some of the problems are big, some are little. If we apply the same process to all these problems, that really helps us in our problem-solving abilities. And with that, I will stop, and I think we have about 10 minutes. Kathy, if anybody has any questions.
Hey, Terry, this is Claude. Kathy had to step out. Can you hear me okay?
I can hear you fine.
All right. Great stuff. Thanks for sharing. So far, no questions. So I encourage you, if some of you have something you want to ask, go ahead and type it in. Or if you have an experience you'd like to share or something that's worked for you in your plant. These little systems, little things you can do can really save some time. I would add, you know, for hardened concrete properties, or I'm sorry, hardened concrete issues down the road, it's always nice to know what form it was poured into and where that form is in the plant. You know, even something like that. Like if you have a plant layout where you have your form and your form numbers, sometimes, you know, there was an issue we were working through on cracking, early age cracking, that related to the placement of the form in relation to the placement of a heater, or maybe by the garage door, or, you know, so suddenly you find a trend in something like that. And it just takes a minute to do a layout and have that documented, so you can always go back and try to figure it out that way. All right, so while I was talking, I did get a couple of questions. Why the Harley logo?
Well, since I never have time to write it, at least when I'm doing presentations, I can at least look at it and pretend that I'm on the bike.
Oh, so you have one, but you don't ride it.
I have one that I ride about 5,000 miles a year.
Okay. All right. What was the outcome of the concrete that showed up at your lab in Cambridge, the one you just mentioned?
They had to double batch in that situation, and they double batched one load of water and admix, but not all the other materials. So they essentially ended up with a double batch of admixture, and it put the concrete to sleep. It was a low cement, high slag mix, so easily retarded in the first place.
Interesting.
Yeah, we had to cook that concrete to make it set up.
Okay. Putting you on the spot here real quick, but through all your years, Terry, of troubleshooting and trying to figure out, is there one specific issue you remember working on that was so unique, you know, or so frustrating, and you finally got to the end, or just something, you know, a story that sticks out that had an interesting outcome?
Well, there's lots of stories. I mean, we're talking almost 40 years here, Claude. But if I can generalize instead of being specific, sure. I would say that that the most frustrating problems that I deal with are the problems that occur and then go away before you can find out what's happening. And you know, those tend to cycle back and forth. I had one problem that was an air issue with a customer that would show up and it would go away, and then, you know, 8 months later it would show up and then go away, and show up and go away. And I don't want to give the conclusion to that, but we finally were able to grab material samples on the day that it showed up, and then get some samples, you know, a week later when it wasn't occurring, and we were able to identify finally after, it must have been 7 or 8 years of going through this. We were finally able to determine what the issue was and stop that from happening. The most frustrating thing in dealing with problem solving is, though, really, we often start the process without enough information. That's right. My experience. We don't get enough information at the beginning, and we often are chasing the wrong rabbit down the wrong trail, and we end up just wasting a lot of time doing that. So I'm a big fan of having a process and collecting data. If I could put in a word here and say that if you're not doing unit weights as part of your testing program, I think you're missing a really big opportunity to track consistency. Unit weight gives you probably more information than any other test that you run.
Well, that's very interesting. That's a good point. Okay. Yeah, and I would add that each of these issues is an opportunity. Once you've been able to go through it, it's an opportunity for training. It's an opportunity to circle back and continuously improve your process by training and teaching the people that are affected what happened, why it happened, and then using that as an opportunity. And every single time you see that continuous improvement. So there are definitely opportunities there for quality assurance, for continual training and things like that. So, but yeah, the unit weight thing is a good advice. Anything else? Any other questions from the group or any? With that, any closing comments from you, Terry?
I would just say that if anybody has questions and if they want to email you and you can forward those to me, I'm happy to answer them.
Okay. I can tell you that Terry is one of those people that no matter when I've got a question, and I know how busy he is, or I think I know, but when I send him a question, he's very, very responsive. So definitely use him as a resource, and us as well. If you've got any questions about this webinar or any issues that you want to discuss, please let us know. So Terry, on behalf of NPCA and the members, thank you very much for taking the time today. Always great to hear you speak. And to everybody out there, any other closing comments?